All right, boys and girls, welcome back to the drive-through. I hope everyone is having a great day as we venture into the final chapter of the first semester of Algebra 1 here in the Innovation Lab. Big. Okay, so there isn't actually a lot for us to do in this, notes section. But it's got to be what is going to lead us through this Chapter 5, so we really have to read it carefully and understand it. So you got Carlos and Clarita, and they are ballers. They're like Marty. They're hustling, okay? And now they're going to get into the pet-sitting summer business. And I know all about how much ridiculous amount of money it costs to have somebody watch your pet. So this is a really good business to be in. So I want you to pause the video, and I want you to read through it. Believe me, it'll make the rest of the videos for the rest of this unit much better. Okay, so what do we have going on? Well, we got a storage shed. That's where they're going to house some of the animals. And we've got a fenced-in backyard where the pets can play. Okay? They have some parameters. A parameter is a limit to something. Okay? So the parameters are space and costs. They can't have an infinite amount of cages because they don't have enough space and they don't have enough money to buy an infinite amount of cages. So eventually I think we're probably going to have to figure out what our parameters are on space. But right now it's just telling you that we have 360 square feet. What is a square foot? It is literally 1 foot by 1 foot. It is a foot square, okay? But here's a question that most Americans would get wrong. How many square inches are in a square foot? Carson?
Well, 1 foot has 12. If you square it, 12 times 12.
Very good, Carson. There are 144 square inches in a square foot. Well, what's a square inch? Well, it's about that. There's 12 rows of 12 inches there. There's 144 square inches in that square foot. So just some things to keep in mind. We're going to have to tap into some of our geometry knowledge in this chapter, okay? You are expected to have understood that by now. I mean, like in your math career, you've had that before, okay? All right, so cat pens require 6 square feet. Dog pens require 24 square feet. Okay? Some other parameters. The Martinez twins only have, well, I shouldn't say only have, they have a nice amount of money to invest into their business. $1,280. This is an important thing to learn. If you want to make money, you got to spend money. Okay? It comes back if you spend it the right way. And it's going to cost $32 for each cat pen and $80 for each dog run. I wonder if that's a day. No, that's just to buy them. That's to buy the cat pens and the dog runs. So we can see cats are smaller and cheaper. The dogs are bigger and more expensive. So let's continue to read. With that in mind, they're only going to charge $8 per day for cats, but they're going to charge $20 for the dogs. Why does that make sense?
Well, I actually realized that they're trying to pay off their cages and their boards off within 4 days.
Oh, nice. So, okay. So each of those, remember that a cat pen, oh yeah, there's no lag there, was $32. We got no more ViewSonic errors.
Yes.
And a dog pen, or a dog run, was $80. So as my boy Carson has wisely noticed, their hope is that after 4 days of getting a dog or a cat, notice 4 times 8 is 32. And 20 times 4, or 4 times 20, is 80. Okay? Alright, I like it. So they're going to charge more for a dog than a cat because it costs more space and money to get the dogs set up. Okay? Now, Mr. Martinez, I think, was this Martinez twins? I think so. Yes. Mr. Martinez has suggested 12 cats and 12 dogs. Carlos thinks they should plan for more dogs because they can charge more. Makes sense. Clarita thinks they should plan for more cats because they take up less space and less time. Well, that makes sense. And as always, math can show you how to maximize your profit. Okay? So, I don't know what kind of recommendations to give to them yet. I got to do some math, and to do some math, I got to learn how to do some area questions, some inequalities. But I would recommend, right now, having done no research, to listen to their dad. Because balance is important, and even though I far prefer dogs, they might need something to eat, so that's what the cats could be there for. I was just joking about that. Okay? Alright, so there's no more notes, but you do need to understand that. And now what I'm going to do for you in the rest of the video is help you out with some of your homework assignments. So here we've got numbers 1 and 2. And the topic, it says, is solving systems of equations by graphing. Okay? Y equals, let's see, it says, substitute the given points into both equations to determine which ordered pair satisfies the system of linear equations. And then graph both equations and label the point of intersection to verify. Alright, so first let's substitute. Put in a 0. Do you get a negative 2? So this one works for the black one. We'll call this the black equation. Put in a 2. Do you get 2? Nope, you get 4, right? So this one doesn't work for the black one. And put in a 1. Do you get 1? And so that one works for the black one. Let's call this the blue one. Put in a 0 for X. What do you get for Y? Put in a 2. Do you get a 2? Yep. Put in a 1. Do you get a 1? So what is the solution to this? C must be the solution. You didn't need to do that. I'm just following the directions, okay? So now let's graph Y equals 3X minus 2, the black equation. What's the Y-intercept, Carson? Negative 2. What's the slope?
3.
So over 1, up 3. Over 1, up 3. Over 1, up 3. Uh-oh. Well, that's just a heat error. I don't even know. Uh-oh. Wow, now they, Alright, so I'm going to try to make a line out of this, although that's not always easy. I want it to start there. Oh gosh, it's just too fine. Too fine. Oh, I'll do my best. Alright, that's kind of our black line, okay? Nope. Now, let's get some blue points on there. So this blue line is actually Y equals 1X plus 0. Okay, so the Y-intercept is 0. And we go over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1. Okay, so if we go to our line feature and turn it to blue, we're going to go from corner to corner. That's what the line Y equals X looks like. Okay? Now it says, graph the equation and label the point of intersection to verify the solution. Where do they intersect, Carson? 1, 1. I've labeled it. Okay? So, number 2. Again, we'll call this the black equation, and we'll switch it over to red this time. Bearcats. Alright, black equation. Put in a 2. 4 plus 3, so that works. Okay? Put in a negative 7. Negative 14 plus 3.
No, it should be negative 11.
That doesn't. It should be negative 11. So that doesn't work for the black one. Put in a 0. 0, 5?
Yes, it works.
I don't think so.
No, it doesn't.
Does not work. Now let's go to the red equation. Put in a 2. Do you get a 7?
Yes.
So that's going to be our intersection point. Put in a negative 7. You get a negative 2. That doesn't work. Put in a 0.
5.
So that works. So this must be our point of intersection. Okay? Black line first. What's the Y-intercept?
3.
We need to clean this board. We got a big spot there. It's even hard for me to... Alright. Y-intercept is 3. The slope is 2. So there's one there. Does it look like I'm doing that right, Carson?
Looks good to me.
Thank you.
Better than what I do anyway.
Let's get that started at a better spot. This is the hardest part, is just getting it. Ugh. I think this is why I miss my good old days of a straight edge. But I can't use a straight edge on this board because it's heat sensitive. So I'm just going to do that, okay? You got to use a straight edge on your test.
Yeah.
All right, red one. What's the slope? Don't tell me the slope is x. What number is in front of that x? Very good. It's 1. There's a 1 there. Okay? Mathematicians are what? They're lazy. That's where math comes from. So that's why they don't write a 1 there, because they're lazy. Okay? Just remember that. All right, slope is 1. So over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1. Can't use a straight edge, which just breaks my heart. So it's going to look something like that. What is the intersection point? Looks to me like it's 2, 7. Okay? You feel good about that, Carson? All right, let's do some different types of problems. A theater wants to take in at least $2,000 for the matinee. Okay? Children's tickets cost $5 each. And adult tickets cost $10 each. The theater can seat up to 350 people. Up to. Okay, so if we add the child in attendance plus the adults in the attendance, it must be less than or equal to what? What is the most amount of people, adults and children, okay? Does that make sense?
Yeah.
Now, let's figure out the restrictions or the parameters on our cost or our profit, our income. How much do we make per child ticket? Right? How much do we make per adult ticket?
10.
And what are we hoping for?
2,000
At least 2,000. So this must be greater than or equal to 2,000. Okay? Find 5 combinations of children and adult tickets that reach the goal. All right, we're going to need a chart here.
What about if we did 349 adults?
Children, adults, cash. Okay? What's your first one?
349 adults.
349 adults.
And 1 child.
And 1 child. Okay? All right, what's 349 times 10? 3,490 plus 5. So we'd love to have a lot more adults than children, right? That's way over 2,000. Let's give me one that might be more realistic.
150 adults.
150 adults.
children.
And 200 children. 200 times 5, 1,000. 150 times 10, 1,500. So this would be $2,500. There's two that work. That's actually very realistic. Okay? A couple adults come by themselves. Every other adult takes their kid. We can do that. All right, give me another one.
How about...
Let's do the most profitable possible example. Let's say we show an NC-17 or a rated R theater show. How much money are we going to make?
3,500.
Okay. All right. You come up with another one.
Okay, we're gonna have a PG. We're gonna have some parents who go see a rated R film, but with some children.
Okay.
We're gonna do 300 adults.
300 adults and 50 children. This has got to work. If this one works, then that one will work, right? So 300 times 10 is 3,000. 50 times 5 is 250. $3,250. And give me one more that you think might be close, Carson.
We're gonna do.
Let's try this. See if that's enough. Okay? That's going to be 1,750. What's 175 times 5?
It works.
What do you get total?
875.
875 here, plus 1,750. 2,625. So those are 5 examples of something that works. Give me one that definitely doesn't work, Carson.
0 adults and 350 children.
What do we make for that?
We only made 1,750.
And this just gives you an idea of what businessmen have to think about. How do we get something that is family-oriented, but make sure that we get plenty of adults? Okay? All right. So hopefully that helps. This is definitely, there's more coming on this down the road. All right, now, look, this is just a question that's weird. It's not hard. Now, you can make it hard. So, it says, use as many of the following shapes in any combination as you need to try to fill in as much of the 12 by 12 grid as you can. Okay? Well, I could do this. 1, 2, 3, and then all the way down. All the way down. All the way down. I could just do 3 times 12. I could do 36 A's by themselves. That'd be a fast way to answer this question.
Would it possibly be a good answer?
I mean, I don't know how to define what a good answer is, Carstiggity. Okay? Let's change my palette a little to try to get these to match. I could do this. 1, 2, 3, 4, 5, 6. All the way down, all the way down, all the way down. There's going to be 2, 3, 4, 5, 6. 6 by 6, I could do 36 E's. Right? I'll do one more that's not all the same one. I could do like 6 E's. 3 A's. I missed Tetris. You get the idea, right? So you can do this any way you want. If you're bored and love to doodle, then make some amazing Tetris piles out of these things if you're Ethan Gauss, okay? But if you're just in a rush and you don't feel like playing Tetris on your math homework, then just get it done. Can I get a boom?
Boom.
Can I get a boom? Boom!